Hello guys, and welcome back to Introduction to Number Theory. This time I would like to discuss an elementary proof of Fermat's small theorem. But first let me remind you what is the statement of this theorem. So we have a prime number p, and we denote the set of all prime numbers this way, a capital P, a nice capital P, and we have an arbitrary integer number a. Well, here I say that it is positive integer, but it doesn't matter actually. And we know that a is not divisible by p. And in that case, the Fermat's small theorem claims that a to the power of p minus 1 is congruent to 1 modulo p, which means that the remainder of a to the power of p minus 1 is equal to 1, where we mean the remainder when divided by p. Well, we already know a proof of this theorem which involves group theory. Now I would like to show you another proof which is mostly elementary. For this purpose, we will consider all remainders modulo p except for 0. Well, just write them down: 1, 2, 3, and so on, p minus 2, p minus 1. So we know that all these numbers are remainders, and all of them are mutually prime with p. And multiply each of them by a. So we gain a, 2a, 3a, and so on, p minus 2a, and p minus 1a. Well, we have a set of p minus 1 numbers, of another p minus 1 numbers, and I claim that remainders of these numbers are just the same and as in the first column, but maybe in another order. In order to prove that, we need to make sure that all these numbers give different remainders when divided by p, because we understand that the amount of these numbers is exactly p minus 1, just the same as here. And if we prove that all of them give different, pairwise different remainders when divided by p, then from this it will follow that the set of remainders of this column is exactly the same as the set of remainders of this column modulo p. Well, consider any two of these numbers, say xa and ya, where x and y are some multipliers from this column. And suppose that xa and ya appear to be congruent modulo p. This means that xa minus ya must be divisible by p. Here we can transform it into x minus y multiplied by a, which should be divisible by p. And we know that since a is not divisible by p and p is prime, we know that a and p are mutually prime. So from this, it follows that exactly the first factor, namely x minus y, must be divisible by p. So it follows from here that x minus y must be divisible by p. But this, how is this possible? Well, I believe that this is possible only if x is equal to y, because both x and y are less than p, greater than 0. So x and y are from this set, well, one of them is x and one of them is y. So if we want x minus y to be divisible by p, then they must be equal. This means that initially equal numbers, equal products were taken here. So any two different numbers from this column give actually different remainders when divided by p. After understanding that, we can take these two sets, the first column and the second column, and we understand that the set of remainders here is the same as the set of remainders here, and we multiply all the numbers in the first column and gain p minus 1 factorial, and we multiply all the numbers in the second column and we gain p minus 1 factorial multiplied by a to the power p minus 1, because there are exactly p minus 1 a's in this column. But these numbers, of course, are not the same, but they give the same remainders when divided by p, which means they are congruent modulo p. And now all we need to do is to get rid of this coefficient or multiplier p minus 1 factorial. We can use Wilson's theorem, because Wilson's theorem states that p minus 1 factorial is congruent to minus 1 modulo p. Well, we haven't proved Wilson's theorem yet, but we still can use it because our proof in future will not involve Fermat small theorem. But nevertheless, I would like to give an explanation that does not involve Wilson's theorem. We can use the same method as here, actually, because if we take these two numbers and transform this congruence modulo p into a difference divisible by p, then we will get p minus 1 factorial multiplied by a to the power of p minus 1 minus 1, and this product should be divisible by p. Well, since p minus 1 factorial is the product of numbers that are mutually prime with p, then itself it is mutually prime with p. So we can conclude that the second factor is actually divisible by p, and this means that indeed a to the power of p minus 1 is, well, I will write it as a divisibility, but we understand that this means exactly the claim of Fermat's small theorem. So this is the general proof, which works for all prime numbers p. Well, maybe some things should be done differently if p is equal to 2, but prime number 2 is always an exception, so we'll not discuss it now, because the Fermat's small theorem is very obvious in that case. What I would like to do now is to show how this proof works in a certain case. Take a certain p and just look at these sets of numbers. For instance, p equal to 7. Well, it's a quite convenient prime number. So first we need to write all the remainders. 1, 2, 3, 4, 5, and 6. And then, well, we need to pick number a. Let's say a equal to 3, which is of course not divisible by 7, and multiply all these numbers by a. So we gain 3, 6, 9, 12, 15, and 18. And now consider remainders of this second column, modulo 7. So, well, 3 is 3, 6 is 6, 9 is congruent to 2, 12 is congruent to 5, 15 is congruent to 1, and 18 is congruent to 4, because 14 is divisible by 7. And now we actually see that all these remainders are present here. Well, let me just connect them. 3 and 3, 6 over here, 9, which is actually 2, it's over here, 5 is over here, 1 is all the way up there, and finally 4 is over here. So we have actually permutation of these remainders. So after multiplying both these sets, we will have, as shown before, two numbers that are congruent modulo p, and after dividing this congruence by 6 factorial, which is of course mutually prime with 7, we will gain that 3 to the power of 6 is congruent to 1 modulo 7, which is exactly the statement of the Fermat's small theorem.